So today's lesson, we're looking at the last chapter, or the last exercise in chapter 16. It's position and average velocity. So just while we start to talk about a couple of the bits at the beginning here, let's think back to what Reese just did in his demonstration for us just then. So people that are maybe watching this at home that haven't been in class for that aren't going to know what we're talking about. But Reese has done a fabulous demonstration of some straight line motion for those people that have missed that. Some things that you are going to need to know, okay, for today's lesson. We've been looking at average rate of change so far. We've been looking at instantaneous rate of change. We're going to look at applying this to velocity today, okay? So average velocity, our formula we're looking at for this is the change in position over the time elapsed, okay? So it relates very closely to, it's pretty much the exact same as your average rate of change formula. So where you're working out average rate of change before, your average velocity in that sense, you're going to be calculating in exactly the same way, okay? The only difference that we're going to look at today is, I suppose, analysing that straight line motion that Reese just demonstrated for us, what that looks like, and the graphs for that particular type of motion. Some things, I suppose, with this, obviously maths and physics go hand in hand, and parts of methods, there are some pretty practical applications of what you're studying in physics. This is, I suppose, rates of change in that sense are one of those things as far as straight line motion goes, things to do with acceleration later on. A lot of the things that you learn in physics, the formulas and stuff are based in this type of maths, okay? But what we were looking at before, Reese was walking backwards and forwards for us in a straight line, similar to what we've got on the page here. We said that he started in the middle of the room, okay? So if we think about where Reese was starting from, it's this middle point that he was starting from. It's our reference point. And at any point on his straight line here, when he was walking, we could say that he was a certain distance from that center point, or I suppose we could make that his position, okay? His position was a certain distance away from our reference point, our origin point. If we think back to what Reese was doing, we had 2 points that he was walking between in this particular example, and they were pretty evenly spaced out. But what he did first was he walked forwards at a constant speed. So he walked forward at a constant speed. As soon as he got to this table, he changed his direction and he came back. And what he was effectively doing is just walking at this constant speed. As soon as he reached that point, he was turning around, okay, like what the pen's doing on the page there at the moment. The second example that we looked at was where Reese started at that constant speed, and then as he started to approach that point, he started to slow down to the point where he stopped, and then he accelerated back up to a constant speed, and then he started to slow down again, and then he accelerated back up to a constant speed, and he kept doing that effectively over and over again. If we think about what that motion looks like if we start to graph it in relation to his position away from the origin point or the point of reference with respect to the amount of time that it was taking, we could sketch two different graphs for those two different types of motion, okay? First graph that Reese, or the first type of motion that Reese was taking, he was walking at a constant speed until he hit the end of that first table. Okay, and so that constant speed, because it is constant in that sense, it's going to be a straight line. So that first motion, or that first bit walking forwards, he's walking in a positive direction away from his center point, and so it's at a constant speed, it's in a straight line. Okay, once he reached that point, he then started walking backwards. So he started to come back toward his middle point at the same rate. Okay, we kept that same constant speed. And once he reached that middle point, he then continued away from the origin point in the same direction until he was about the same distance away. Okay, and he's kept that same constant speed the whole time. To finish off, he changed direction again. So straight away, he changed his constant movement and came back toward his reference point, finished at his reference point. Reese actually kept going a little bit. We had this zigzag type of graph going, and he just kept sort of zigzagging as he went around. But for the first bit where he walked forwards, walked backwards, walked forwards again, this is what we would say his position versus time graph look like if we make position this axis here and time this axis here. Okay, so as this is changing, Reece is walking forward, so he's walking in a positive direction, constant rate. He then started to walk backwards, so he got back to his point of origin, walked past the point of origin, then changed direction again and came back to his point of origin. Okay, key thing there, because he was at a constant rate the whole time, we're keeping it a nice straight line. Second type of motion that we could try and draw here, again, it's going to be a position versus time graph. This time though, because he started to slow down around those points where he turned around, so same thing, he started to turn around about here, he came back, he ended up back at the origin here, he turned around again somewhere around about here, he walked in a positive direction to start with, okay, and because he started to slow down, what we start to see is it starts to be a little bit more of a curve that with a maximum point there that starts to happen, as opposed to just being that straight line motion. Okay, and what we can see here, he's got this section where he's pretty well walking at what we would say is a reasonably constant speed. It maybe is because he is starting at that speed and then he's gradually starting to slow down. Maybe over time he's slowing down that for that whole period. He gets to a point though where he's slowed down enough to just stop, okay, before he turns around and goes in the other direction. He then starts to accelerate back up to what was pretty much his constant speed, and then he slows down again when he gets back to that far point, and then starts to speed back up again to get back to his point of reference. Okay, so I suppose the difference between our two types of graphs here, if you're maintaining a constant speed the whole time, you're going to maintain that straight line graph as far as position versus time goes. If you are changing your speed, you're going to start to see that you get these curves involved. Okay, so when you're looking at position versus time graphs, this is kind of what you're looking for, some of the features that you're looking for that are going to be described to you. Okay, so think back to Reece walking backwards and forwards across the room and think about what type of motion he's making. Okay, remember with this, the most confusing thing people find at times is they see these graphs where people seem to be moving around all over the place, but we're actually just referring to Reece walking backwards and forwards in a straight line. Okay, when he's walking backwards, he's going to be taking stuff off his graph. When he's walking forwards, he's going to be adding stuff to it. Okay, making it positive or making it negative. What we're effectively going to look at doing now is looking at average velocity. So over this particular part of his graph here, obviously with a constant sort of period, we can look at looking at his average velocity. It will be his constant velocity, as we talked about with our average rate of change, comparing it with a constant rate of change. But when you start to get parts that are curved in that sense, it can be a really useful thing to be able to estimate what's going on, to be able to work out your average velocity. So same way that we were working out average rate of change, where we were looking at change in position, change in y over change in x, what we're now going to be looking at is change in p over change in t. Okay, and that is going to tell us what our average velocity is. Same thing if we're going to put this into function notation. The average velocity will be your change in your interval, so a over b, over function subbing b into your function minus subbing a into your function. Okay, so we're going to look at, I suppose, a couple of examples where we can use that particular knowledge. So if s of t equals t squared plus 3t, and this is the position function of a particle moving in a straight line, where t is the time in seconds and s is displacement or position in meters, find the average velocity for the time interval 1, 2. So first thing that you know when you get this is that you're going to be using the average velocity formula. So average velocity, and we know that we're dealing with function s here, so it's not going to be s, it's going to be t. We're going to be looking at s instead of f, sorry. S of b minus s of a over b minus a. This is going to be your formula that you're looking at. So you're going to need to be able to find both an a and a b value from this so that you can substitute those into your formula. What we're looking at here, a is the first part of our interval, b is the second part of our interval, so a will be 1, b will be 2. So you're going to be looking for s of 1 and s of 2 when you're solving for these to begin with. Can we get Kaz out just for a sec, please? We're going to have a look at sketching a graph of this just to demonstrate to us what's going on. So if you have your Kaz out and look at putting that function, t squared plus 3t, into your Kaz. squared plus 3x. So let's just put that. Okay, so if we can sketch that particular function in your CAS, what do we notice about this function when we sketch it? What are some key points? I suppose if we're looking at our CAS here, what are some key points on our graph? Yeah, intercepts, what are they? -3 and 0. Good. So if we draw a little rough sketch of what this might look like, just over here, we've got this function that comes through here. It goes through the origin in that sense, and that's a pretty average looking parabola. Let's say we sketch this. We've got an intercept here at -3, and we've got an intercept here at 0. Okay, which part of this graph are we actually interested in? Okay, good. We want the positive for both P and T. In this case, you could have a negative P that you're looking at, but we only want this side of your graph here. Okay, want the positive values of T. So all of this stuff here isn't really going to be of any use to you, okay? Because it's before the time T equals 0. We're only looking at time as a positive variable in that sense. The other thing, if we look at this particular graph, we're looking at the average rate of the average velocity over the interval 1, 2. So we're going to be looking at a couple of different points on this graph at 1 and at 2, or T equals 1 and T equals 2. So if we sketch a little bit more of a meaningful graph for ourselves here, P and T, we're kind of looking at this part of the graph that looks a bit like this. We want a value at 1 and a value at 2, okay? Finding those we can substitute in. So up here, we're going to want to find S of 1 and S of 2, just to start with. So S of 1 is going to be 1 squared plus 3 times 1, which gives us 4. S of 2 is going to be 2 squared plus 3 times 2, which is going to give us 10. 4 plus 6. So we can put these in, 4 and 10, okay, onto your graph. So what we're effectively looking at, what this question is asking us to do, is it's asking us to find that average rate of change between these 2 points here. So we could really sketch that in. And the average rate of change over these 2 points is your average velocity. Okay, so when we work out what the gradient of this line, it's a little bit hard to see on that video there, but average velocity between those 2 points is your average rate of change. We're using our average velocity formula, so substituting in average velocity equals S of 2 minus S of 1 over 2 minus 1, which gives us 10 take 4 over 2 take 1, 6 over 1. And so your velocity, or your average velocity in this point over that interval is 6 meters per second, okay? So you can calculate that average speed that the particle in that case, so the particle is moving at. Particles are quite common. You'll see a lot of particles in your textbook for this particular topic. But yeah, the particle is moving at 6 meters per second from that time T equals 1 to T equals 2. Okay, so that's effectively one application of average velocity. You can substitute into these formulas to find that. What I would like you guys to do is have a look now at finding the average velocity for the same particle over the interval 3, 5. So if you can have a go at that now, just in your workbook. So we're going through that same process that we've just taken here. You're just changing your interval though to 3, 5. So just have a go at that. When you're done, have your hands on your head for me. We'll look at moving on. people finishing. That's good. Just another minute or so. All right, so just to check now, we've got a solution on the bottom here for you to check your work against. So average velocity, first thing you need to know S of 3 and S of 5, so you can substitute those into your formula. S of 3 is 18, S of 5 is 40. Average velocity will be S of 5 minus S of 3 over 5 minus 3. So 40 take 18 over 2, 22 over 2, which gives you 11 meters per second. Okay, so the particle is moving at 11 meters per second over that interval from 3 seconds to 5 seconds. What this means is you can write meters per second like this, Heidi. So meters per second, m over s. S here is to the power of 1. When you bring it up and you make it ms, you raise it to the power of -1. It's an index law thing. It's just a notation for meters per second. Yeah, you can write it m/s. That's fine. Yeah, it's just a physics notation thing to write it ms minus 1. Okay, some applications.
In physics, it's more common to write it m over s because then you don't have to change it when you're writing meters per second squared.
Okay, yeah. When I did physics, it was ms minus 1 and ms minus 2. So maybe they've changed that, or yeah, might be a little bit different, just depending on who your teacher is, maybe. Okay. Last lesson we looked at instantaneous rate of change. Okay, an instantaneous rate of change was the rate of change that's occurring at any given instant. Okay, so not over that interval that we looked at for an average, but just at the very point. This is exactly how the function the function was changing at that point in time. For instantaneous velocity, it takes on exactly the same sort of meaning. All it's looking at is you're looking at a position versus time graph, and if you look at the gradient of the tangent line at any particular point, or you work out that average rate of change over that really, really small interval, like what we did at that particular point, okay, it's telling you the actual velocity of something at that time. So if you think about when Reese was moving across the room there and he started to slow down, we could work out Reese's average velocity over his walk to the table. And because he slowed down at a particular point and he was walking at a constant rate, maybe at another point, the average velocity is just going to be the average that he was walking for the entire time there. But what we could look at is if we stopped him midpoint, or we sort of freeze framed at a midpoint in his walk, okay, and analysed how fast he was actually walking at that actual point, that's our instantaneous velocity, okay? So instantaneous velocity is when you're looking at a particular graph and saying at that particular point, the rate of change is exactly equal to this. What we look at then with velocity versus time graphs is you can use a velocity versus time graph, or you can use a position versus time graph, to help you sketch a velocity versus time graph by analysing the gradient at particular points, or analysing the instantaneous velocity at particular points. So if we look at this particular graph, and I've just said particular a hell of a lot in a couple of sentences there, but if we look at this graph, The position versus time graph for a particle moving in a straight line is shown. So this is kind of Reese, he's walking backwards in this particular part of his graph here. The gradient of the curve at various times is indicated on the graph. So Reese starts off, he's walking backwards at 2 meters per second. He's then slowing down to 1 meter per second as he approaches his turning point. He turns, and so he's actually physically stopped here. He's then accelerating back up, so he's now walking at 1 meter per second, and then he finishes getting back to his origin point. He's walking at 2 meters per second at that particular time. Okay. What we can do with that information now, we can make a table of values and we can look at plotting those. So at time t equals 0, 1, 2, 3, and 4, we can look at how fast he was moving. We can read that off the gradient of the graph here. So at time t equals 0, Reese's velocity was minus 2 meters per second. At time t equals 1, it was minus 1 meters per second. At time t equals 2, he's here and his gradient is 0. T equals 3, he's walking at 1 meter per second. And t equals 4, he's walking at 2 meters per second. Okay. What we now have is we have a set of coordinates that we can look at plotting. So we've got this position versus time graph, which is a nice quadratic here. And what we're then going to do is we're going to sketch a linear graph which is showing his velocity over that period of time. So we can show v versus t in this particular graph. And we're starting at t equals 0. We have a velocity of negative 2. So 0 minus 2. We get to t equals 1, and we have a velocity of minus 1. We get to t equals 0. We have a velocity of t equals 2, sorry. We have a velocity of 0. So I've got that round the wrong way. So t equals 2, and we've got a velocity of 0. T equals 3, velocity of 1, and t equals 4, velocity of 2. Okay, so as we get to t equals 4, our velocity is 2. So this is showing us how Reese's instantaneous velocity is changing over time. Okay, and so what we could say here is that he is going through a period of constantly decelerating back down to moving at 0. And then he is constantly accelerating back up to another speed here. Okay, so because this is a straight line on your velocity versus time graph, it's telling you that there is acceleration or deceleration that is happening as you approach 0, or move away from 0. What it's also looking at showing you here is if you consider your position versus time graph, where we have this minimum in your position versus time graph, what can we see happening on your velocity versus time graph when we get to a minimum on your position versus time graph? Yeah, it's stopped and it's showing you that you have an intercept on this particular graph here. Okay, so where we have this quadratic graph up the top and we have the minimum at x equals 2, when we convert this to a velocity versus time graph and we get a straight line, it's where your x-intercept is going to be. Okay, and so you have an x-intercept where you have a minimum with your position versus time graph. Okay, what you can see here, we have a negative gradient at this particular point leading down to our minimum. Because we have a negative gradient, this particular part of your function is negative. Where we're positive here, we have a positive gradient, we're accelerating again. This particular part of your function here is positive. All right.
So if the gradient is
Yep. Gradient's negative, your velocity is going to be negative at that point. Okay. Gradient is equal to 0, or you have your turning point there. Your velocity is equal to 0. Gradient's positive, your velocity is going to be positive. That's that link we want to try and make between these two types of graphs. Okay. What else do I want to tell you about velocity versus time graphs? Let's maybe move on to the next one and then we can come back to anything I think I've forgotten. So what we're going to do here, we've got a couple of different things. Which velocity versus time or which velocity graph corresponds to the position graph. So velocity versus time graph, position versus time graph. We've got a position graph here and we've got a collection of different velocity graphs. What can we do to help us identify which velocity graph should correspond to this position graph? What are some key features of the graph to start with that we're looking for? Reese.
They're accelerating in a positive direction.
Okay.
Or like decelerating in a positive direction and then accelerating in a negative direction.
Okay, good. So this particular part of your graph here is positive. So the first thing that we want to look for is we want to look for a velocity versus time graph where the beginning of the graph is positive. So we can cross this particular function here out, we can cross this particular function here out, and we can cross this particular function. No, sorry, we can't cross that one. That one's positive too, sorry. I'm looking at a negative line. So this one here, we're in the negative. This one here, we're in the negative at the beginning. So we can cross those ones out. These ones are all positive at the beginning. Next thing or next feature, I suppose, that we can look at to help us out here. What are we looking for next? What are some key features of that graph?
The maximum. Yeah.
Maximum point, it's occurring at m is equal to 0 is occurring at 2. So what we want to see is we want to see this crossover point at our axis here, okay? Where we have our maximum is where we're going to have an x-intercept in our velocity versus time graph. The other key pieces of information we can look at the beginning, so time is equal to 0, we've got a gradient of 12, okay? So your velocity at that particular point is 12. The other thing that you're looking at is it's a negative 12 when time is equal to 4. Okay, so when time is equal to 4, we're at negative 12. So all of those features are helping us to identify C is the correct graph, and we can cross out both B and E. Okay, so you're looking at your values of your gradient, you're looking at whether your gradient is positive or negative to help you decide which position graph would correspond, or which velocity graph would correspond to that position graph. Second one is going the other way, okay? Which position graph responds to the velocity graph here? So if we're looking at this velocity graph, what are some key pieces of information we can use to start with? Yep. So the x-intercept happens at 2 here. What will happen then when t is equal to 2? Yeah, it's going to be where we have that point. It's either going to be a maximum or a minimum. So looking at that, we've got a maximum or a minimum at all of our graphs here. Okay, so it's not really helping us to start with. What else can we now look at to try and determine which graph we would be looking at? Okay, this is it's a negative rate to begin with. Okay, so we're looking for a negative gradient. All you can see here is that this one starts with a positive gradient, so we can cross it out. This one here also starts with a positive gradient, we can cross it out. This one here, positive gradient to start with, so we can cross it out. Okay. All that this is telling us, it goes from positive to turning point to negative, sorry, to turning point to positive. So we've got negative, turning point positive, negative, turning point positive. We actually don't have enough information at the moment to be able to decide which graph is the one that we want, okay? Because it's not telling us anything about the position yet. They could both be it, yeah. But if we stipulate with this that position begins at the origin point, which graph now must we be looking at if, yeah, A, okay. A, because position is starting at 0, if we place that stipulation on it, both of these graphs are showing the same thing, they're just starting at a different position. As soon as we say position starts at 0, we're looking at this particular graph here now, okay, because we want the graph where the position starts at 0. This particular point here, it might be, say, 5. If position started at 5 and they stipulated that in the question, you would then be able to say, well, it can't be A because A is starting at 0. We are then therefore looking for B, okay? The actual motion is being modelled in the same way here. The position, the starting point of the particle, the ball, the person, whoever's moving, Reese, is the same, but he's just starting at a different point in both of these graphs, okay? So there'll be an opportunity for you to have a bit of a look at analysing position versus time graphs, velocity versus time graphs, deciding which goes with which. And that's, I think, an important thing for you to be able to do conceptually, to be able to visualise what's actually going on. For people that are much more sciencey, this is something that you generally tend to grasp a lot quicker. For people that are much more abstract maths, it does take a little bit of thinking, it does take a bit of practice, okay? And that was definitely me when I was in your shoes. It took me quite a while to get my head around what actually happens here, okay? Any questions on any of that so far that people want to ask?
So, I
Yep.
still wonder why it's not C.
Why it's not B, you mean? It's A. C, this one here. So what we're looking at here is your velocity at the beginning is a negative velocity, okay? So if you're moving in at a negative velocity, you're actually moving backwards,
So do you
all right?
think
So if you're moving at a negative velocity, you're moving away from the origin point in a negative direction,
that's not
okay?
So does it mean that the graph is going this way, or you mean that the graph has to be below?
This one here, we need to have a negative gradient on our quadratic, on our other thing. So what we're looking at here you have a negative gradient on this quadratic, okay? And that negative gradient correlates to the fact that you've got a negative velocity, all right? Here you've got a positive velocity, and it correlates to the fact that you've now got a positive gradient. This one here, on the other hand, though, it's got a positive gradient to start with, so you would need to be above your axis and then coming down to be below your axis. So this velocity versus time graph for C would look something more like this. Okay? That, okay. The one that's above? Yeah. We'll stop that there if you